Hello friends, welcome to ashatech.com. Today we discuss the Bernoulli's equation. And in the derivation of this equation, let us consider a pipe with a varying diameter and height through which an incompressible fluid is flowing. The relationship between areas of cross-sections A, speed V, height from the ground Y, and the pressure P at two different points 1 and 2 is shown in the figure below. This is point number 1 and this is point number 2, and we are considering flow along the streamline, and here we are showing one streamline on a flow tube of a fluid mass. Assumptions taken is one, that the fluid involved is a liquid which is ideal and incompressible, meaning that its density is constant. Also, that the energy of the fluid is conserved because it is assumed that no viscous forces are acting on the fluid. The flow is steady and continuous. Flow is along a streamline and it is one-dimensional. The uniform velocity is what is the velocity on all the sections and is equal to mean velocity. The only forces acting on the fluid are gravity and pressure forces. Therefore, as the fluid moves from point 1 to point 2, there is the work done by pressure force, and we are denoting it as dW. As dW. So as the fluid enters the flow tube at point 1, there is a pressure force F1 that is meant to do the work in displacing it from point 1 to point 2. But likewise, at point 2, there is a pressure force that acts in opposite to force F1 that is opposing the displacement of the fluid as it is leaving point number 2. Therefore, here is force F1 in the direction of flow, and this is F2 opposing the displacement of the fluid from point 1 to point 2 as it is leaving the flow tube. We have to also note that as the fluid is moving from point 1 to 2, there is a change in the gravitational potential energy, and since Y2 is above Y1, then there is a work done, negative work done on the fluid in moving it from point Y1 to Y2 against gravity. Then 2, there is also, as it changes from the velocity of the fluid changes from V1 to V2, there is gain in kinetic energy. So to begin with, we know that if dW1 is the work done at point 1, it is equal to the pressure force. In other words, it is if the pressure force at P1 is F1, the dW1 is equal to F1 times the distance dx1 at point 1 moved by the fluid mass. And therefore, if F1 is equal to pressure P1 times the area at 1, the cross-section area at 1 is A1, and since F1 is equal to P1 A1, then the work done dW1 by pressure is equal to P1 A1 dx1. But looking at this expression, A1 dx1 is equal to volume of that mass, small mass, at point 1. and that is dV1. Therefore, dW1 is equal to P1 dV1. This is equation 1a. Similarly, there is a force F2 which is opposing the displacement of the mass as it is leaving point 2 of the flow tube. Therefore, let us take work done by that force F2 to be dW2 to equal to that force F2 times the displacement of the fluid mass, the x2. Likewise, F2 is equal to P2 times A2. And substituting it in this equation, the W2 is equal to P2 A2 dx2. Therefore, A2 giving A2 dx2 as volume dV2, then the above equation becomes the W2 equals P2 dV2. And this is equation 1b. The total work done, therefore, total work done on the system is the W equal to the W1 plus the W2. But we must also consider that when F2 acts on the fluid, it acts opposite the direction of flow. Therefore, considering that concept, the W2 will therefore equal to negative P2 dV2. Total work done by pressure, the W is equal to the W1 minus the W2, which is equal to P1 plus minus P2 dV2. Since flow is incompressible, then dV is equal to dV1 is equal to dV2. The volume of the mass at point 1 remains constant throughout from point 1 to point 2, and therefore substituting that in the equation given in the equation above, therefore the W is equal to P1 minus P2 brackets dV. Let us call this equation A. Let us also talk about the negative work done by gravity, and it is du. So this du is equal to small mass dm times gravity times vertical distance above datum at point 1 being y1 minus the small mass dm times g times, this should be at y2, this should be y1. Since the m is equal to the density of the fluid times the small volume, then it means that the du will equal to rho dV into 2. Let us recall that du is equal to P2. Kinetic energy decay is equal to a half dm V2 squared minus a half dm V1 squared. Since dm is equal to density times volume, then decay is equal to rho dv into actually over 2 rho dv over 2 into V2 squared minus V1 squared. This is equation C. If that is equation C, from work energy theorem, whereby work on the system, work done on system is equal to the change in kinetic energy of the system. Therefore, the total work done on the system is due to pressure and the negative work done by gravity, which is P1 minus P2 cross brackets dv, then minus low dvg into y2 minus y1, which is low dv out of 2 into v2 squared minus v1 squared. Rearranging and dividing both sides by low dvg will give P1 minus P2 out of rho g minus y2 plus y1 is equal to a half over g into v2 squared minus v1 squared. Rearranging this equation, P1 over rho g plus y1 plus 1 over 2g v1 squared will equal to P2 over rho g plus y2 plus a half 2g times v2 squared. The equation is Bernoulli's equation. And therefore Bernoulli's principle is valid. Since points 1 and 2 are chosen arbitrarily, this equation can be rewritten as P over rho g plus y plus a half over g v squared is equal to h is equal to a constant, whereby this is the pressure energy per unit weight, this is the gravitational potential energy per unit weight, and this is the kinetic energy per unit weight of the system, and this is the total energy of the system, in terms of head.